Today's subject is coupled linear hydroelastic analysis for a floating offshore wind energy substructure in its frequency domain. Here is the schematic description of a floating offshore wind energy substructure published in Namei's paper in 2023. The wind force is first transferred to the blade and nacelle assembly, and the force is transferred to substructures. And here the substructure is subjected to wave motion, and to keep its position we need to put mooring lines here. Actually, dynamic analysis of mooring line was explained in another video. Please refer to the video if you are interested in the dynamics of mooring line. And then the force caused by wave motion is best prescribed by the velocity potential. We'll explain the velocity potential later. And the velocity potential consists of this incident potential, and once the wave is touched to structure, and then there is diffraction wave. And diffraction wave is described by so-called diffraction potential. And then another potential is developed by the motion of substructures. This is called radiation potential. And then to analyze the structural behavior of substructure, we have to consider the wave load, and then the wind thrust, and then the mooring forces. In this slide, I don't want to consider the mooring forces. As I explained, the mooring forces were discussed in another video. Please refer to the video regarding the analysis of mooring forces. In this video, I'd like to talk about the analysis of wind load, wave load, and analysis of wind thrust applied to the substructure. First, let's talk about the Galerkin method. In standard Galerkin method, the equilibrium or balance equation is given by the principle of virtual work. And simply speaking, the kinetic virtual work done by the inertial force should be equal to the difference between the virtual work done by external force and then the virtual work done by internal forces or stress. The kinetic virtual work is given by the inertial force, mass, density times acceleration, and then the dot product over the virtual displacement. And we need to integrate it over the volume, entire volume. And then here we have, if you want to consider the pressure here, the pressure is applied only the wet surface of the structure. That's why the traction is equal to the pressure times, and then the normal to the structure. Because we take as a convention the compressive stress as the positive pressure. That's why we have to choose the direction of normal. It's the inward to the structure, what I mean, outward from the fluid. And then again, we need to integrate over the virtual displacement using the dot product here. So make sure that this integration is only for the wet surface of the structure. And then the last term is the internal virtual work. Internal virtual work in hydroelasticity, the modulus matrix double dot, the strain is equal to stress value. That means the work done by stress over the virtual strain here. This is internal virtual work. The overall work balance should be satisfied in the principle of virtual work. And then to derive discrete equations, here we have to discretize the displacement, the virtual displacement, and then the real displacement using interpolation. In finite element method, the interpolation is called the shape function. Here we follow the standard finite element method, and please refer to my lecture note regarding the finite element method. The displacement field is function of coordinate x and then the time. And then according to standard finite element method, we separate the nature of function according to spatial coordinate into the shape functions, and then the time function is kept in the nodal displacement. Here u sub I are the nodal displacement. If you take the derivative of the displacement over an element, we can obtain the strain distribution too. Here the b is the symmetric part of the derivative of the shape function. This is well known, the B matrix. So if you plug this displacement and strain into the principle of virtual work shown in the previous slide, we can obtain the well-known discrete equilibrium equation. Here Mij is the mass matrix, and the U double dot means this is the acceleration. U sub j means acceleration of node j. And then here the Kij is the stiffness matrix of the node. And then make sure that here I have boldface for K because that represents all the DOF, the kind of vector. On the right hand side, we have discrete forces corresponding to the applied pressure. And then make sure that here Cij is a damping matrix. It is widely accepted that we can represent the damping matrix as a linear combination of mass and the stiffness empirically. And this is a discretization using the compact shape functions. The compact shape function means the shape function or interpolation functions are defined within elements. Rather than these compact shape functions, we can consider the global shape functions. Here, the above figure is an example of compact shape function. In the case of compact shape functions, the shape function is non-zero only in associated elements, otherwise it is equal to 0. That's why we call the compact shape functions. But also we can consider global shape functions. In the case of this one-dimensional problem, we can consider, for example, Fourier series, or we can consider polynomials. We can consider various sets of the global functions. And then we can superpose these global shape functions to approximate the displacement. For example, here, let's imagine I have a blue curve here. The blue curve is given by psi and x and alpha. The alpha is associated for mode alpha. So if you choose modal deformation as the global shape functions, and then we can consider alpha is equal to 1 and alpha is equal to 2, 3, 4, 5, 6, as many as we want. Then we can superpose the behavior of the eigenmode. We can approximate the displacement. This is how we use the global support. And then for general structures, it's better to use the eigen deformation rather than the Fourier series. That's why in most cases we choose eigen deformation as the global shape functions. And another benefit of using the eigen functions, the dot product between different eigenmode is equal to 0. They are orthogonal. And then here we have very interesting property. Let's imagine that the black line is representing the bottom of the structure, the floating structure, and then we can define normal. And then here, at each point of deformed structure, we can obtain the vector of the modal displacement. If you calculate the dot product between the modal displacement and then the normal of the pressure, then we can obtain a quantity at each point of the structure. We want to call this N alpha. So I'll tell you where we use this quantity later. Okay, so if you use the eigenmode as the shape functions, we can interpolate the displacement using the eigenmode of psi alpha, and then each eigenmode is associated with modal displacement zeta here. So alpha and alpha here. The repeating index means sum of it. So for example, we can consider the mode from mode 1 to mode 10 or mode 20, blah, blah, blah. Traditionally speaking, the mode 1 to mode 6, they are for the rigid body mode. And then further, so make sure that this is a continuous function. This continuous function further can be interpolated using the compact shape functions. Here, if you introduce compact shape function here, so we can interpolate this continuous modal displacement using the compact shape function. That means here this value is the nodal values of the modal displacement. And this is the final expression of our interpolation. Displacement x, u, x, and t can be interpolated like this. Shape function and then modal, the nodal values of modal displacement, psi, I, alpha, and then we need to consider the modal displacement zeta alpha here. So if you plug this displacement into the previous principal virtual work, we can obtain the modal form of modal matrix and then modal stiffness matrix and then the modal displacement. Here asterisk in the superscript means the modal one. This is a modal one. The relation between the mass and then the modal mass is given by this equation, and the stiffness too. This is stiffness obtained from the conventional finite element method, and then if we multiply the modal displacement in front of the stiffness matrix and then back of the stiffness matrix, and then we can obtain the modal displacement. modal stiffness matrix, and then also modal matrix similar to the calculation of modal stiffness matrix. And then modal external forces will be similar to the modal the nodal external forces were calculated in conventional finite element method, and then we multiply the modal vectors in front of these external forces, then we can obtain modal external forces F alpha star. And if you plug here, the zeta alpha is function of time. So now we are talking about harmonic motion. If wave loading is harmonic, and then the displacement becomes shows harmonic behavior too, but it must have some phase shift. That's why we can express the modal displacement zeta alpha using C alpha and then the harmonic part. So this is C alpha. Doesn't have C alpha has only the phase shift and the magnitude of the modal displacement, and here the exponential I alpha t, and that has what? That has the harmonic motion of the behavior. So if you plug the zeta alpha to this expression, because this is what second derivative of zeta beta with respect time, and because here we have I alpha, that means we're gonna have minus omega square. And then also the first derivative of zeta beta as shown here, then it becomes I omega here. So similar to this, if you rearrange all the equation, finally we have these equations. Now let's talk about how we calculate the wave force. So make sure that if you consider the linear wave, then we can describe the distribution of velocity of fluid using the velocity potential. For incompressible fluid, the divergence of velocity is equal to 0. So if you plug in the expression of velocity is equal to the divergence, the gradient of potential into that equation, we can obtain the governing Laplace equation. The second Laplacian of velocity potential is equal to 0 at any point of fluid. Now, because this is a linear, the velocity potential can be considered superposition of 3 different potentials. The first one is the incident potential, so wave of potential far away from the structure. And then the second part is diffraction potential. Now this is the potential diffracted by the existence of structure. And then the third term is the disturbance of potential caused by the displacement of the structure. Because the velocity potential is also, it shows harmonic motion. That's why we multiply the exponential I omega t here. And that's the boundary condition. On the surface of water, we need to satisfy this equation. And then at the bottom, the velocity potential should be equal to 0. On the bottom, the velocity of wave should be equal to 0. And then to the structure for each mode of potential, it should satisfy I omega n alpha. And I already showed you the definition of n alpha. Where is it? The definition of n alpha is given by this equation. And then this is the relation between the incident potential and then the diffraction of potential. Because by the diffraction for fixed structure, the direction of incident wave is opposite to the direction of the diffraction wave. That's why we have minus sign here. Now let's talk about how we integrate the pressure on wet surface gamma W here. The pressure is given by a Bernoulli equation. The second term is hydrostatic pressure, and then the first term is the dynamic pressure. And then if you consider the velocity potential is the spatial term times exponential I omega t, if you get the time derivative of the potential, so you're gonna have I omega naturally. That's why it is given the pressure is equal to second equation. Pressure is equal to minus rho W is the mass density of water, and the I omega and the potential, and then gravity acceleration, x3. x3 is the coordinate in the vertical direction. And if you plug the pressure into the discrete force, here I have shape function, and then here my the modal displacement, and then I have pressure here. So if you plug this information of pressure, then we have n alpha as we define. The modal displacement dot product, the shape function is equal to n alpha at this position. This is the discrete force. So make sure that here the gray line represents the initial position of the structure, and then here the black dark deformed curve means the modal displacement. And then eventually, so if you plug that information of the velocity potential to that equation, because the pressure is equal to the equation is given by the Bernoulli equation. Let's plug in here, and if you solve this integration, finally we can obtain a term associated with omega square, and then the second term associated with I omega, and then a third term associated with just 1 times C beta, and then the external force, and then exponential I omega t. And then here A alpha beta associated with omega square is called added mass, and then the term associated with I omega is called added damping, and then the term associated with C beta is called added stiffness. If you plug this external force to the previous equation, then finally we obtain this equation. So make sure that if you move everything to the left hand side, and this term is added to the mass term. That's why we call this is added mass. And then the term I omega, this is associated added to the damping matrix. That's why we call this is added damping. And then similar to this, the term added to the stiffness matrix is called added stiffness. So if you consider the only wave motion, then we can calculate the modal displacement C beta, and then C beta has the information of the magnitude of the modal displacement and also the phase angle. The phase angle can be calculated from the complex numbers very easily. Please make sure that the C beta is a complex number. The A stands for is the wave magnitude. Now let's talk about how we deal with wind force. Okay, let's consider one-dimensional case. The thrust force can be given by quadratic thrust in one dimension. Here, rho A is the mass density of air, and the Ct is thrust coefficient. The area is acting area. For example, the rotor area here. And then because this is the thrusting force is quadratically proportional to the wind speed, we need to consider relative wind because the nacelle point is moving with a certain velocity. We need to calculate the relative velocity. That's why relative velocity is the velocity of wind minus the velocity of the rotor point. So here for simplicity, I want to call 1/2 rho A, the thrusting coefficient A is B wind here because this is constant. And then the speed of wind is what? The superposition of the mean velocity and the fluctuation of velocity Vf. So make sure that V mean velocity is a constant, and then Vf is a fluctuation. Usually the fluctuation is small compared to the mean velocity, and then it's a minus of the velocity of the structure. Okay, so now let's expand this equation. The square and also square, and then the linear terms, and then also bilinear terms. We have 3 different bilinear terms. If you take out V naught square, and then we have 1, and then Vf divided by V naught square. So I already told you that the fluctuation velocity of the wind is small compared to the mean velocity. That's why square of small things is very small. That's why we can drop the first term at the second term. And then third term too. the speed of structure is also very small compared to the mean velocity of the wind. That's why the square term of this, the third term, can be dropped. And then also the last term, also small thing times small thing. That's why we can drop. Finally, we have only three different terms. The first term, and then the fourth term. The fourth term is what? The fourth term is the thrust force caused by the fluctuation of the wind with respect to initial velocity. And then the third term is the negative thrust force caused by the displacement velocity of the structure over the initial mean velocity of the wind. So we can approximate in one dimension. A thrust force consists of three different terms. The thrust force caused by the mean wind velocity. The second term is the thrust force caused by the fluctuation of wind velocity over the mean velocity. And the third term is thrusting force caused by the velocity of the structure over the mean velocity. Okay, so in three dimensions, we need to consider a vector. This is nk stands for the normal direction of the rotor point. And then for each point, we can calculate the thrust force vector like this. Here v naught means the speed of the mean speed of wind, and then here the vw vw is equal to the direction of wind times the direction of rotor, and then here the n beta is, as I defined it, this is the modal displacement times the direction of normal in that direction. So let's plug this thrusting force to the expression of the wind. Here, because we only have a limited number of points, the thrusting force is applied to that points only. So if you rearrange all the equation, finally we can obtain this equation. So again, we have exponential terms. So we can drop the exponential term. We can cancel the exponential term from the left-hand side and right-hand side. By the way, note previously I have three different terms for the thrusting force. But make sure that the first term is constant. That's why the behavior of structure associated with the first thrusting force should be calculated from a static analysis. For dynamic analysis, we have to consider only these two different terms. Here I showed you, the two terms associated for the two thrusting terms. The first one is the term for the velocity fluctuation. The second one is the term for the displacement of the structure. Okay, so finally, if you add up all the terms together, the right-hand side I have wave force, and then the wind force here. And then if you look at left-hand side, we have another term for the wind action. So if you solve this equation, and then we can obtain the modal displacement for coupled effect of wave and wind for elastic structure.